Hello and welcome to Nautel's webinar on the introduction to the RF toolkit, the radio coverage tool, a bit more depth. I'm going to try to answer a lot of questions today about this exciting tool and to provide a lot of good information. I noticed that we've got people from all over the world online, and we're grateful for people coming from Greece and from Indonesia and from all over the world. We had one of the highest registrations for this webinar of any webinar that we've conducted. We're very happy and pleased about that. So here's the agenda for today. Our guest today, a very important guest, is Mr. Roger Coudet, who's an amateur radio operator and a retired RF broadcast engineer in Montreal, Quebec. He's VE2 DBA. Hello, Roger.
Hello. How do you do?
Nice to have you with us today.
Thank you.
And so here's the agenda of what we're going to talk about. We're going to talk about what the Nautel RF toolkit is, how does propagation analysis work and what are its limitations, what can the Nautel Radio Coverage Tool do, where to find the coverage tool, and then we're going to spend most of the time of today's webinar actually working through various scenarios and showing you how you use the tool when you set it up. As always, you can ask questions online. We will go back and answer all the questions when the webinar is concluded. If we don't answer all the questions before we have to leave, we will reply to you by email. But please do ask questions, and we may even open, if we have some time, we may even open it up to asking the listeners to suggest various things we can plot, and we'll have some fun with that. So what is the Nautel RF Toolkit? Well, as the title infers, it's a set of tools designed to help both technical and non-technical people easily understand complex systems. It allows users to analyze possible transmitter locations, tower heights, antenna gains, and transmitter power levels for coverage. And while it's based on solid engineering principles, these tools cannot and will not replace the services of a qualified consultant. And we'll mention that several times through the presentation because it's important to understand what the limitations of the software are. How does it work? Well, it's based on solid engineering and the Longley Rice ITS algorithm and covers most VHF, UHF frequencies. Roger, what are the actual frequency ranges that you can utilize this software to predict?
The model is valid from 20 megahertz to 20 gigahertz, but I would say it has been proven to be quite good in the VHF and UHF range.
Okay.
I don't know too much about the rest.
All right. So that means something in the neighborhood of 30 megahertz to 3,000 megahertz.
Yeah.
Okay. Very good. Or 30 gigahertz. Okay, very good. So it shows a typical map, and we're going to show you how to create one of these maps and how to extract the graphic from this map and utilize it. One new tool, a very cool thing. Last webinar we did back in August, one of the questions that came in suggested that it would be ever so much more useful to him if he could know the approximate population within the coverage areas. So if you'll notice here, we've actually added that. And Roger added that within, what, 24 hours of the last webinar, Roger?
Yes. I found the United Nations database.
Yes.
And I included that in the calculation.
So now you can actually look at the amount of population within a specific coverage area. And again, that's a worldwide thing, of course, with varying amounts of accuracy. Is that right?
Yeah. From country to country, they submit their information to United Nations. So depending on the country, you have different level of quality, let's say, or precision.
Yeah. Okay. Very good. So now let's continue on. So it uses a digitized terrain database, which is available from NASA, which is called SRTM, Shuttle Radar Terrain Mapping. And this database covers the entire Earth with higher resolution in the more populated areas.
Yeah, just one word about that, Chuck. The original extend from -60 to +60.
Right.
But we added the rest of the world with other source. So we still call it SRTM.
Yes.
But we have more than SRTM in our database.
And what kind of accuracy are we talking about, Roger? What kind of, how often geographically are the samples taken and how close are they?
The database itself, again, depends on where you are in the world. In North America, we are always at least at 1 arcseconds, and in the US, you have third arcseconds, 1/3 of an arc.
So 1 arcsecond in the U.S. and in North America, and 1/3 arcsecond in the United States. Now, for most people who are not used to dealing with arcseconds, approximately how much distance are we talking about?
Yeah, 1 arcsecond is about 30 meters.
So what that says is that there's actually a sample of the altitude at a particular location every 30 meters, every 100 feet.
Yeah.
That's pretty amazing.
But
and then when you get out of North America, what happens?
Yeah. But this is the database. When you do a calculation, there is another compromise that is done by the algorithm.
Yes.
As an example, if you select a certain range in a certain picture size, then you're limited to the resolution of that choice.
Right, and that's shown on the model as we go through the software.
Yeah.
Right. What kind of accuracy do you have in third world countries or less populated areas?
It's 3 arcseconds, so 100 meters.
Okay, and another question would be, how big in terms of data storage does this database require to be stored, or how much data have you got stored here?
Oh, I don't have the latest figure, but I will say it's about 300 gig, and it's compressed. So uncompressed, let's say it's close to 1 terabyte. Wow.
Okay. That sounded like a lot of storage until I could go down to the store and buy a 1 terabyte drive for $80 these days. Okay, so let's talk about, there's 2 primary parts of this tool. There are coverage predictions over an area, which is the traditional coverage prediction, and then point-to-point analysis. So where would you use these? Well, in a radio or television environment, if you were doing the coverage mapping of your station, well, that's the prediction over an area or coverage prediction, and point-to-point would be for an STL or a microwave link of some kind. And so this shows how this is the profile view of a link, and you can see here, this is my house in Nova Scotia, and I'm going over St. Margaret's Bay here, and there's an Aspettagon tower on the Aspettagon Peninsula, and you can see that this link was at, well, it doesn't show the frequency, but you can see here the Fresnel zones, the first Fresnel zone, second Fresnel zone, and the third Fresnel zone. So this is a very basic understanding of what the point-to-point link looks like. The radio coverage tool is based on software which was developed by our guest, Roger Coudet of Montreal. For more information, you can find a website where you can download this software for free from this website. So write this down, and we'll stay on here for a second. It's a wonderful tool, Roger, you've developed, and I've been using it personally for almost, what, 15, 20 years almost.
Yeah.
It's amazing software, and it really is revolutionized the way people are using this kind of propagation analysis. So you can find the radio coverage tool, Nautel's implementation of this, on the Nautel homepage, or you can go directly to www.nautel.com/RF toolkit. When you do that, you have to get an ID if you're not already a NUG member. You can get an ID for free. You can register online, and once you do that, here's the things that it will allow you to do again for free. See the estimated coverage of an FM or TV station. This is big news. We just started this yesterday. Plot it against a map and save the generated map. You can see the estimated population living within the coverage area, as we discussed. And you can plot an STL path and see if it's likely to be reliable. And we're going to walk through those scenarios today. So let's just go ahead and do that. Let me switch around here, and we will switch to the radio coverage tool. Now, I'll probably have to log in again here because it's been a while since I logged in, and I probably logged out. So I will log in now, and I put my information over here and my password, which it remembered. So I log in, And now I can go to the Radio Coverage Tool. And this is the main screen that we'll be visiting over and over today. So let's take a look at how you would create a new transmitter site first. So Roger, right now we've defined, because of the way we're going to do our models today, we've defined Denver as more or less our home. But we could be anywhere we wanted to be. Let's figure out how to create a new location. So for instance, we have a customer, a listener, a viewer on the air from Indonesia today. So let's go down to Jakarta and create. Let's see if this is going to work.
You're going to play with your side.
Nope, I got to go the other way. I got to go over to this way because otherwise it shows up in the wrong spot, I think. And so we can zero in here and place cursor at the center. That's wrong. Got to go the other way. There we go. Place cursor at center. Nope. Place cursor at center. There we go. Now we have it. So now I'm going to go zoom in on Jakarta, and I will place the cursor at the center and there in Jakarta. And now I'm going to submit a new transmitter site, and I can name this Jakarta, and I can add it to my transmitter sites. So now I've created a new transmitter site. We can take a look at the sites we've already created. We created one on the Lookout Mountain near Denver. We created one in a studio near Denver, another studio in Arvada, and now we have our new one in Jakarta. So we can modify these as well. If we happen to know the exact coordinates of our location, we can come in and plug them in here. And where you might get that information, well, for instance, if you go to Google Maps, you can click on a location and you can see the exact coordinates in the form that the system is looking for it right there. So you can zoom in. You can even use Street View and see the exact location and get it very precise, and then you can drag and drop that information or cut and paste that information in here and modify your sites and name them what you want to name. Does that make sense so far, Roger, or have I missed something?
Yes, just one comment is
Yep.
if you work in an area of the world, you can define it as your home. So next time you create a site, it will be from there.
That's right. That's right. And this is what we've done for Denver to make it a lot easier for us to do this. So now we would create, let's do a point-to-point link first. Now we would create a new point-to-point link. And hopefully this is going to, we've had a few problems with speed. Sometimes if there's a lot of people using the system, it slows down just a little bit, and we've had a lot of use recently. So it's taken a little bit of time there. Let me click it again. So we're gonna define a point-to-point link, and well, I'm having fun. Let me do this and restart it. See if that helps. Murphy's Law, Roger. or Parkinson's corollary. Have you ever heard of Parkinson's corollary?
Oh, no, that's a new one.
Yeah, basically, simply stated, it is Murphy was an optimist.
Okay.
Okay, so let's take a look at my point-to-point links. And here's some ones we've already defined, so we can take a look at them. This is a link we defined, which is an analog 950 megahertz STL. And we'll look at the information we inputted. We inputted the locations, of course, which are down here. We went from the studio in Denver to the transmitter site on Lookout Mountain. And the latitude and longitude are shown for both of those locations, as well as the ground elevation, that is the height above sea level in meters. And then the antenna height, we assumed about a 100-foot tower or 30-meter tower at both locations. Here's the azimuth from Lookout Mountain from the studio to Lookout Mountain, and this is from the Lookout Mountain to the studio. And then here's the tilt in the same direction. So you can see because there's a substantial difference in elevation that there's a substantial tilt. So you'd want to adjust your antenna accordingly. Now here's the specifics. We're using a 20-watt STL at 950 megahertz. We assumed a 1 dB line loss in the transmitter side. We assumed an 18 dB gain in the antenna. I'll show you where that came from. It comes from this brochure here from Scala, and you can see here that the PR950, which is a popular antenna, has an 18 dB gain. So we'll go back here. We plug that both in at the receiver and the transmitter. There's our line loss for the transmitter, and our receiver sensitivity actually comes from a receiver STL. In this case, we used the Marty STL SR20, and you can see here that for 60 dB signal-to-noise ratio, we've got 14 microvolts required of signal strength to make that work. So that's approximately 14 microvolts of signal there. Now, when we calculate what's called the path loss, we have the free space loss, which is calculated based on the frequency and the distance. Is that the only two features to that, Roger?
I mean, the total path loss includes the free space plus if there is an obstruction, it will show up there. Forest and urban are dependent on the existing land cover.
Right.
And the statistical loss is caused by the 70% choice. That is the default value in the program.
Right.
You can change that. But it's a way of being a little bit pessimistic compared to the original model.
That's one way of phrasing it. We had a good chat about this earlier, Roger. When we talk about being pessimistic, what we're really talking about is headroom or margin in the system design so that our reliability is enhanced.
But
right?
My experience is that based on my measurement in the field, if you put 70% reliability, the default value,
which is here,
most of the prediction fits your measurement.
Right. And in this particular scenario, with the way that we've set it up in a 23 kilometer path, we're looking at a 34 dB fade margin. So that means that the received signal, which is 704 microvolts, exceeds the required signal by 34 dBu, or 34 dB. And so that gives us a relatively reliable path from the receiver, or from the transmitter to the receiver site, which is at the transmitter site in this particular case. So this is showing a standard analog STL. And let's see if the system is working a little bit more robustly now, and I can show the actual information that we would put in to create that. Yeah, now we get it. So here's what we would have done to create that. You've got your sites here. So we were actually from studio to transmitter site that way, and it was 30 meters at both locations. And then we would have named it here. We put up the frequency of 950 megahertz. Transmitter power is 20 watts. The line loss was 1 dB. Transmitter antenna gain was 18 and 18. And line loss 1. And we went to 14 dBUV and the required reliability. So this is the exact scenario that we set up in order to create what we just looked at on the other sheet. So now let's go back and let's try a different scenario. Let's try looking at the same thing but substituting, oops, I went the wrong way, sorry, back here. We're going to do my point-to-point links. This time let's use a standard IP link, and this is not a specific product. This is kind of a typical for an IP link type of thing. So let's look at this. Here is an IP link. And what we're looking at here is those same two sites. Make sure that that's right. Yep, it's 23 kilometers here. And we're looking at the transmitter power and the line losses. We've got 20 dB antennas, and we show a total fade margin of 2.65 dB, which is, as it shows here, is yellow. it's not very good. And particularly since with a digital IP link, if you get below the required fade margin, it just dies completely, as opposed to fading slightly like an analog link would.
Yeah, but don't forget that this is based on a threshold of a high speed link.
Right.
What happens is that the link will reduce speed.
That's correct.
And then you will get a better fade margin.
Okay, that's a good point. That's a good point. All right, so let's take a look and see how we could. One way to fix this link would be, for instance, let's go back to my links, reduce the distance. So in this particular situation, what we've done is to move the studio, and let's view that. And the other parameters are exactly the same, but we've moved the studio, if you look down here, to Applewood, near Arvada, Colorado. And that link now, instead of being 23 kilometers, is 10.2 kilometers. All the other parameters are the same, and our fade margin is up to 11.29 dB, which is classified as green. Now, whether that's enough in your particular scenario to make the system be considered reliable is up to you, but this does provide a almost 12 dB fade margin. Anything to add there, Roger?
Yeah, that in this case, if you want something more reliable, you can increase the antenna size.
Yes.
Like it's a 20 dB dBi now. We can have at that frequency we can have more. We can have
and that actually, antenna gain is a really good way to improve the performance, because in that situation you're actually reducing interference at the same way. The spot in the sky that you're illuminating, and particularly the spot of the sky that you're receiving from, is reduced.
Yeah.
So it improves your freedom from interference as well. One other thing I'd like to talk about for a second, Roger, are these colors on this profile. Here we have kind of green down here, red down here in this little dip, and green again, then red down here, and it also has some height to it along here. Can you explain what those are?
Okay. The color on the ground is the signal level if the side 2 were located there. So if you take the receiver on the right side, on the right side,
Mm-hmm.
and you move it on the path. So it shows, if you start from the left side and you
Yes.
go to the right side, okay?
Yes, yes.
On your way, you will see that the signal is good about
Oh, I see what you're saying. Down here, yes. Uh-huh.
And then you lose the signal, and when you go on top of the mountain, then you get the signal back.
Okay, so presumably the reason it starts up right here is because it's above that spot which was blocking.
Exactly.
Okay.
So this is something that is not really useful for this particular study, but if you're in an other type of study where you want to find how close you have to go to get the signal,
Yes.
it would be nice to have that.
Okay,
The typical color are the land cover.
okay, so the other color here is the land cover, is what you're saying?
Yeah, the one that are on top of that line.
Yep. And so explain land cover for a second. In addition to this massive database of 1 terabyte that we have that is the height of every particular spot, we also have land cover data. So can you explain what the land cover data is and how it works?
Yeah, if you look at your mouse now, you're just above a blue area.
Mm-hmm.
Okay, and this is a small city. The red is ice scraper.
Okay.
And you see also dark green near the top. Yeah.
Yep.
This is pine trees.
Right.
So
Which you would expect near Lookout Mountain.
You don't see much of it here because the topography is so large.
Right.
If you have a shorter link, you could see better the land cover. In this case, the land cover has almost no effect because it's way below the beam.
The path, that's right. That's right. Is there other information here that would be useful for people to see? What is this precision number here, Roger?
Yeah, that's it means that the extraction of the data was done every 10 meters.
Okay.
So we have what we could call extrapolation. We have more or interpolation. We have more points than the database can offer, or we are at the we are better than the database. It means that we do not lose information.
Okay. Okay. All right. Very good. All right. So that covers point-to-point links, I think. Oh, and we've gotten all three of the scenarios there, so that should be that. Let's talk about creating a coverage plot. So let's talk about creating a coverage plot here. This is a station that we'll create on top of the Lookout Mountain site that we set up already. We put in the frequency, the antenna height above ground. We put in the transmitter system. Now notice here in the transmitter system we've got lots of pre-calculated systems. So we've got a 40 kilowatt with a 6-bay omnidirectional antenna, an 8-bay, a 10-bay, and we've got lots of choices all the way down to 200-watt transmitters or 300-watt transmitters. And here's where we find the television, but we'll show that in a little bit. And of course the television transmitter can do other systems, but the only one we've implemented so far for this analysis is ATSC. And then we have the receive system. Now there's a lot of choices here. The FM car receiver assumes that what you're looking for is where you could hear it in a car, where a lot of people listen to. See, we're focused on a relatively low gain antenna, relatively close to the ground. And then there's other standards that the FCC and others use, like a 54 and 60 dBUV standard, or a 60 and 70. In Europe they use a couple of standards, a 54 and 66 or a 54 and 74. And then for television, we use a 41 and 48 in the U.S. as your coverage standards. So now let's go back and hit cancel and look at one of the coverage plots that we've already calculated. So the first one is a 1 kilowatt FM transmitter, 4-bay, to a car radio. And let's view that coverage plot. And so it calculated a lot faster than if we had entered it ourselves. If we had entered it ourselves, the database has to go and calculate all the data, and that's probably a good time to go get a cup of coffee. But this is a 1 kilowatt FM transmitter located on Lookout Mountain, and you can see the 44 dBu coverage is light green, and the 34 dBu coverage is out to all the yellow areas here. And what's really cool is it's showing us not only the coverage on the map, but it's also calculating the number of square kilometers which are covered in the 44 and the 34. So you can see 15,000 square kilometers in 44 dBu coverage and 25,000 square kilometers in 34 dBu coverage. And then there's the population. And again, Roger, you said this is coming from United Nations data.
Yeah. And as an example, in the US, I think the numbers are quite good. In Canada, it's I would say a bit less quality, and it depends where you are. So we cannot guarantee it's good in your place, but this is the best information we can have for free.
That's right. That's right, and it's useful in the sense that you get an idea of how many people you might lose or gain if you make changes in your system within a particular coverage area. So now, how would I use this data? Well, I can actually zoom in and out and move it around just like I would be able to in Google Maps. But in addition, if I move this a little to the right, I can take and pull this up. Now, this provides all of the information that we used when we created this particular model. So you can see it's a 1,000 watt transmitter. The transmitter line loss was calculated at 1.1 dB. The receiver threshold was configured for a typical car radio receiver. The antenna height is 1 meter above ground, about 3 feet, and the antenna gain is minus a half a dB. The frequency is 103 megahertz. The location is that coordinates. required reliability, strong signal margin, those sorts of things are all there. So what's neat about this is I can actually, if I want to, I can actually hit the print screen button on my PC here, and I think there are similar buttons in an Apple Mac or something like that, and I can come over to Irfan View. Now I'm going to open it up so you can see my Irfan View. This is just a standard off-the-shelf freebie graphics application, and I'm going to paste this picture into Irfan View. So I just did a screenshot in Windows from the software on the web page, and then I pasted it here into Irfan View. And then what I can do is I can draw a little box around this part and isolate just what I want to see, hit Control Y, which is crop, and now if I hit Control Z, I can paste that into anything, or I can save it as a JPEG, or I can do what I want. So I have a document that includes all of the reference information that's inside, the map showing the coverage, as well as all the details about what those coverage areas represent, both in terms of signal level, square kilometers, and population estimates. And by the way, we went back and looked under Wikipedia and checked out the Denver metropolitan area, and this number does seem to track properly with that information from Wikipedia. So let me minimize or get rid of this screen for a second, and we'll go back to this screen here. And now what we can do is, let's do one more thing here. Let's go take a look at, let's go return to my coverage plots, and let's see the same thing, but instead of a 1 kilowatt with a 2-bay or 4-bay antenna, let's do a 40 kilowatt with a 6-bay antenna. Let's look at that coverage plot. Now instead of just getting up to Fort Collins, you can see we're all the way up past Cheyenne in Wyoming and all the way down to Pueblo instead of just barely making it to Colorado Springs. And the population has grown considerably as well, and you can see this was 25,000 kilometers before, and it's now over 70,000 kilometers for the same signal strength. So you can see how this works as well, and again we can play the same trick and move that in, and we can move this over and create a document the same way. So that shows how that works. And let's do one more. Well, actually, before that, I want to show you another neat trick that's kind of hidden in here. And I know, Roger, this is something that you enjoy. So what we've just done is we've downloaded a file from the Nautel Radio Coverage Tool system, which is a zip file. And inside this zip file, and I now have to share that zip file with you. There we go. There's a bunch of things, including a KML file. And Roger, what would you do with the KML file?
This will in fact show your coverage. If you have installed Google Earth on your machine, it will show up on your computer.
Okay, so it's like an overlay to Google Earth.
Yeah.
Okay, and what are the other files here?
So there are other pictures that are also geo-referenced. Okay.
So you're talking about the JPEG file and the PNG file?
Yeah, exactly.
So let me look at this JPEG file here. Let me share that one with you. That's this one. So now what we're doing is we're looking at a black and white, almost a relief photograph showing the mountains in Colorado.
So these are what I call my confidence test. Okay, so I know that this was the data in memory that was used for the calculation.
Good. Okay, and then let's do another one here. Let's go back to the zip file manager here, and shall we look at the population data?
Yeah, the PNG.
Whoops, that's showing, that's not the one we wanted to do. This is showing tabular wires, where that comes from. What are these numbers here?
You're referencing in fact, you can open that in Radio Mobile.
Yeah, let me bring up what this just showed. This is it here. Do you see this one here?
Yeah.
What is this? What is this talking about? This is the DAT file. I hit that one by mistake.
Yeah, that's with each picture there is a DAT file that shows the boundary of the picture.
I see.
And you also have the description, and you see those numbers, the population are showing there as well.
So this is the 40, whatever it was, the smaller signal strength number of square kilometers, and this was the higher higher requirement, and then this is the population for each of those two zones as well.
Yeah, exactly.
Perfect.
So, but now if you open the picture.
Yeah, I will do that. 1 second. Let me close this, and we'll go back to here. And now you want to open which picture?
The next one.
The pop?
The pop, yeah.
Okay, there we go. And let me share that. All right. Now we're seeing, this is presumably the Denver area here, and you can see little, so this is, there's apparently a color lookup table that shows population per square kilometer or something like that, and it's by color.
Exactly. And again, it's a confidence check.
Yes, of course.
What population density were used for the coverage.
Yep.
So the program, in fact, compare the coverage to the density and give the reach population that way.
Very good. Okay, let me close that down. Anything else we should look at in that zip file?
We still have the clutter. So the
okay.
Yeah, that's the last one we should
the
show.
PNG, and I'll share that. Okay, so this is the clutter file. I'll explain what we're seeing here.
So when we were looking at the PAT profiling, we were seeing those pine trees and city and so on. So these are the, in fact, the type of terrain used by the program, and that affects the calculation. If the radio beam goes through those land cover, you will have supplemental loss. In our case, don't forget that we were very high on the mountain.
Yes.
Our radio beam simply goes above the land cover and is not affected.
That's right. There was no Fresnel zone encroachment in the land.
For the land cover to interact with the path loss, it has to be within the first Fresnel zone.
Yes.
So as soon as there is a clearance above the first Fresnel zone, there is no land cover loss added.
Okay, very good. So the land cover loss defines what the program assumes will happen to the signal if it bounces off the earth.
Yeah.
Okay, very good. So let me close that down. I noticed, by the way, Roger, you'll be pleased to hear that we're getting a lot of questions, so we're going to be able to answer a lot of questions here in a few minutes. Let's see here. So, now I wanted to go through and explain what happens with television. Let's look at television too. So we'll turn to my coverage plots, and we'll bring up the 100-watt 4-bay antenna UHF ATSC and view that coverage plot. So that shows what a 100-watt ATSC transmitter with a 4-bay antenna on the top of Lookout Mountain, what it would cover. And it covers the bulk of the population within the Denver metropolitan area, and does pretty well, actually, when you consider the distance here. That's 50 kilometers, and it's going probably almost 100 kilometers out to this point up here.
Chuck, I don't see anything here.
Oh, I didn't share it. I'm sorry. My mistake. There you go. Oops. Wrong one. How about this? That work better?
No, that's not the right one. Okay, now we see. Sorry
yeah, okay.
about that.
Okay. So you can see here the coverage is out to about almost 100 kilometers away. And you can see the number of square kilometers and the population being covered in just a 100-watt ATSC transmitter. That's pretty cool. Okay, now there's one more feature on this system that I wanted to show everybody, an opportunity before we get to your questions. And this is this idea of multiple coverage plots. So when you click on here, let's take these two right here and submit them. And what that does for me is I get both of them on the screen, and I notice here that down here I can click them on or off. So for instance, what we're seeing right now is the 40 kilowatt coverage, and if I would turn off that block, I'm now looking at the 1 kilowatt coverage. So it makes it very easy to see in terms of on the map, and I can even zoom in a little bit, make it a little easier to see. So that's the 1 kilowatt, and that's the 40 kilowatt. Zoom out a little bit, go back in. Yeah. So now we're able to see the difference, and if you look at the square kilometers, it's a pretty huge difference between one and the other. So these are some of the functions that the software provides. Now I know that we've probably raised a lot of questions, and I have a lot of questions on here to answer. So let's take some time and try to answer these questions. A little bit difficult to read here on the way that the system shows it. When doing the point-to-point calculation, what does the 70% required reliability refer to? Roger?
Okay, so based on the test I made in the field, okay?
Yes.
Let's say if you take 50%, that will be no statistic at all. This is the average signal, okay? By putting 70, you make the program a little bit pessimistic.
Right.
And this is what I observe in the field, that if I use 50%, every number that I get from the model is too optimistic. If I select 70%, I see that most of my measurement fits the prediction. So
and those that are off are equally distributed, both optimistic and pessimistic.
Yeah, exactly. So what I did is I used 70% as a default value.
Okay.
And if you use that value, you should see a correspondence between your measurement in the field and the prediction of the program.
Okay. Okay, very good. The next question is, it says you're showing features on the map I did not get when I used the tool. How do I get to the menu at the bottom? Not sure I know specifically. You should be able to just follow exactly the things we just did on the screen and have it work this way. It may be that we've added some features since the last time you used it, and it may be worth trying it again, Dave, and just following the same exact steps we did, and you should be able to get that same information. Another gentleman says, this is very neat. I've played with Radio Mobile a little bit. Is the tool applicable to studying synchronous co-channel FM boosters? And will it display signal strength ratios at locations from 2 transmitter sites? The answer to that is no. The online tool doesn't do that. Radio Mobile does that very well. And there is no cost to Radio Mobile. You certainly can do it that way. It's just that it's a lot more complicated to set up, and that's why we thought that it'd be useful to have an online tool, and we intentionally made this tool more simple. Now, if there are lots of interest in figuring out where SFN interference zones fall, we could certainly, Roger and I could certainly work on adding that functionality at some point in time. Do you agree, Roger?
Oh yes, but it's a lot of work, so yeah, we'll see.
Yeah, okay, fair enough. It says, can you also show how to save a point-to-point link? Same exact scenario. We just we go back to return to multiple coverage. Let me go back. Return to main menu. Look at my point-to-point links. View this link. And then what you're going to have to do is, because this is a very long one, you're going to have to capture sections of it. So we'll come up here, bring it down a little bit to about like that, and then we'll move this so that that's at the top of the screen. And then we'd hit print screen and capture just the point down to here, and then save it as a JPEG, and then perhaps bring this section down here up and then capture it again. Yes, sir.
I think the picture itself can be copied by itself to the clipboard.
Right. You can just right-click on here and say Save Image As.
Yeah.
Yeah. That would work as well.
It's only the numbers that you need to print screen.
If we do that, Roger, does the picture save including the points and the line?
Oh, I'm not sure about that.
I think that's why I had to do print screen before.
I was referring to the upper picture.
Okay, the profile.
This one.
So I could do that, Save Image As, and we could try it and hit Copy Image here, and bring up Irfan View and share that with all of you. Here we are. Now we'll paste that in Irfan View, and yep, there it is. So you could get that easily, using that method. Now let me go back to here, and let's see what other questions we have. Is there a spot to enter transmission line length? If not, how can it be accurate without that parameter? Want to explain how you're estimating transmission line length?
Yeah, they are pre-calculated in your in the program settings. Okay, when you select the type of antenna you're using.
Yes.
We also have a pre-selected line loss, and if you change the antenna height, the line loss will increase as well.
In other words, it assumes a certain length of feed line based on the height of the tower at the site. The difference between the height above average terrain at the site and the height at the top of the antenna.
And we selected the type of coax according to
the power level.
The earth antenna.
Yeah, yeah, okay. So it's a reasonable approximation.
Yeah.
It says, are you assuming circular polarization? The answer is yes. We made assumptions that what we're dealing with here is a circularly polarized side-mounted antenna. And we recognize that that's not always the case. And in radio mobile, for instance, you can actually model directional antennas and antennas that don't act this way, but this is what we use for this particular model.
We have to be careful. Even if the signal is considered as a circular signal, the audience is either vertical or horizontal.
Right.
There is no circular receiver. So
Sure.
We assume that we have a vertical polarization, and we take the vertical gain as the gain of the antenna.
Okay. The next question says, what is opacity?
That's the transparency of the coverage.
Okay.
The way it works is in Google Maps, the map background that we use. Okay.
Yep.
The opacity of the image depends on that value.
Okay.
And it's a limitation of Google Maps. Your
Right.
image has to be already transparent to be shown transparent in Google Maps.
So if it was 100%, you would not see the underlying map, and if it was 0%, you couldn't see the actual plot.
Yeah, it will be opaque at 100 and completely invisible at 0. But if you export as we did before with the zip file, you don't have this limitation in Google Earth. You can
Right.
change the transparency there.
Because it's just an overlay at that point.
Yeah, yeah.
Okay, next question, it says, is the population data feature available for radio mobile as well, or only via the Nautel version?
No, because Radio Mobile doesn't have yet population database on its download sites.
Yep.
And this is something I'm thinking to do someday, but I'm not there yet.
Okay, very good.
So only this online tool has the population.
And we're very proud of that, Roger. It says, the next question, can you customize the transmitter power antenna while creating a plot? Well, you specify the transmitter power antenna out of the pull-downs. Now, we've limited to those specific pull-down choices. And at this point, we didn't get into the situation of having been able to, in the online version, of being able to type in your specific antenna gain or your specific transmitter power. We made various assumptions as to the choices that you might have, and in most cases, if you're close to, if a 3 kilowatt's not going to be demonstrably different than a 2.5 kilowatt, for instance.
Yeah, we did that to simplify the interface.
Yep.
Okay, that's a choice for this particular application.
Yep. Another gentleman is asking a question I think we've pretty much answered, which is, can we make a radio coverage for a directional antenna? And yet that would be a feature of radio mobile, but we felt that it would complicate the development of this online tool. So it's not in the Nautel tool. And what about transmitter power above 40 kilowatts? That's a good question. We can certainly add some. We now have stations on the air with Nautel transmitters running at 88 kilowatts or above, so we could certainly do that. How do you save it as a link so it shows up in My Links? So if we go back here to my new point-to-point link, when you hit submit, it saves it. Well, we can do that. We'll put a new test link, and we'll just leave it with the parameters.
You need the two site.
Yep, I need to put a different site here. Yep, okay. So now I'm going to submit, and then once I do that, it's going to take a while, unfortunately, but once I do that, it's going to give me the opportunity to add it to my links, which I've highlighted here. And so if I want to, I add it to my links, and then when I come down to my point-to-point links, we will see that new test link is there. So that's how you do that. Next question, are you assuming a side-mounted antenna is omnidirectional? And the answer is yes. We don't have the ability here to estimate what kind of impact the tower or other terrain may have on the omnidirectionality of the antenna, or the antenna itself, the non-omnidirectionality. It says, with the high-rise buildings in our city, how accurate is this tool predicting coverage for FM transmission? We can't, the system does not know the specific heights and locations of big buildings in your community, so it doesn't know that. It just makes assumptions based on the fact that it's considered to be a city, and it has a particular effect based on the city losses. Is that right, Roger?
Yeah, this is, let's say, an average building aid, and we have low and high density.
Yep.
But the model itself, we do have additional loss, okay?
Yes.
And it's based on the Hookah-Rama model from Tokyo.
Okay.
This is really a statistical approach. If you want to know if like multipath around the buildings and things like that, definitively not in the model. It's too complicated to calculate. You need a very, let's say, much more sophisticated tool or model to do that.
And I think this is an appropriate spot to underline what we said earlier, and that is that this system is not a replacement for a professional consulting engineer. A professional consulting engineer would be able to give you results similar to this that they derive with this kind of software. However, they would also be able to add their experience and knowledge about this particular area and the way the buildings are, and be able to give you feedback that we can't possibly do from here. So that's why this is just a tool for people understanding wanting to understand the basics of, what happens if I add 100 feet to my tower? What happens if I take my power from 1 kilowatt to 40 kilowatt? What is the rough numbers of things going to look like? And how is this site compared to that site? These are the kinds of questions that the software is pretty good for. In terms of predicting actual coverage in a downtown area or something like that, much, much better to get yourself a professional consulting engineer that does this for a living day in, day out. So, Roger, anything else to add? I think we've pretty much covered everything we intended to do.
Oh, it's okay on my side. No problem.
I thank you very much for being a part of things today. Let me go back and tie the ribbons on this thing for us. So if you want to learn more, you can sign up for our newsletter at nautel.com. This webinar and all webinars are archived at www.nautel.com/webinars. We also have a lot of them excerpted up on YouTube, and of course you can always shop for Nautel parts and some smaller transmitters on store.nautel.com. And the last thing I wanted to say is, if we can ever be of any assistance, feel free to contact us at www.nautel.com, sales@nautel.com, and there's our handsome group of radio professionals ready to stand by and assist you as they can. So, Roger, I'd like to thank you very much for being a part of today's webinar.
Thank you very much.
And I wish everybody a very good day. Thank you very much. Bye-bye.